I'm Mark Arenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's video is a companion to problem number 11, where we calculated the largest product in a particular grid of numbers. In that video, we wrote code in the Netwide Assembly language to solve the problem, but we left the task of outputting the result incomplete. Today, we'll write some more assembly code and then build up the missing piece of our solution from last time. This is a simple Hello World program we wrote last time. Let's break it down briefly. An assembly program operates on registers, and there are several general-purpose registers available to us. This program uses RDI, or RCX if you're on Windows, to pass an argument to a built-in libc function. First, we declare bits 64 to indicate our program is a 64-bit program. Then we promise the existence of our application's entry point called main, and we declare that we'll be using an external function called puts from the C standard library. Our data section consists of the string hello world, which we'll print to the screen. We follow the C convention and terminate our string in a null byte so that we can use the built-in C functions for printing to the screen. Inside our code, or text section, we define our main function as a label. We do a bit of boilerplate stack shuffling to preserve RBP for our caller. Then we call puts. Puts is a function in the C standard library, so it's going to follow the calling convention of your operating system. On a Linux system like the one I'm writing this on right now, the first argument to a function is passed in RDI. On Windows, the first argument is passed in the RCX register. In either case, we store a pointer to the global memory containing our string in the appropriate register, and then we make the function call. Finally, we do a bit more stack shuffling to return to our caller. Now let's review how to write our own function. In this example, we no longer want to print hello world to the screen only one time. Instead, we're going to write a function called print hello to write it to the screen several times, with an argument indicating how many times to print this constant string. Our data section looks identical to before. In our code section, we first write our print hello function. A function is merely a label, like the target of a jump. There's no special keyword in x86 assembly to indicate that a particular label is a function. Inside our function, we do our usual stack shuffling. We'll use RBX for our loop counter, so we should store its current value on the stack so as not to clobber the caller's value for that register. Next, we move our argument into RBX. libc functions pass several integer arguments in registers, and indeed, that would be faster in a real program. But for the sake of simplicity, we'll just use the stack for all arguments in our function. Our argument was pushed onto the stack just before making the function call. When the function call was made, the current value of the instruction pointer was pushed onto the stack as part of the call instruction. Then, inside our function, we pushed RBP onto the stack before saving our new base pointer. Each of these values is 8 bytes on a 64-bit system, so our argument is 16 bytes away from the current value of the base pointer RBP. We don't have to worry about the RBX value we pushed onto the stack, as that happened after preserving our base pointer. Once we have our loop counter in RBX, we begin our loop. Inside the loop, we make a call to puts just like before. Then we decrement RBX. We want our loop to continue as long as RBX is greater than 0. So we compare RBX to 0 and then do a conditional jump back to the top of our loop if the comparison returned greater than. We've reached the end of our function, so we restore the preserved value of the register RBX. Then we pop RBP for the caller and return, just like we would for any function. To call this function, we push the numerical argument onto the stack, and then use the call instruction. The function we've written doesn't pop its arguments off the stack, so after calling the function, it's our responsibility to clean up the stack, in this case by adding the appropriate value to RSP to offset the push instruction we did before the call. Now let's get a bit more practice writing function. We're going to write a factorial function. That is, our function will take a 64-bit integer as input, and will return the product of all integers from 1 up to the input. We follow our previous convention, where arguments are passed on the call stack and return values are supplied back to the caller via RAX. Any other registers our function wishes to use will be saved by the call E. We begin our function with the usual prelude, then we push RCX into RDX. Our function is going to use RAX, RCX, and indirectly RDX, but we don't need to save RAX since we'll be using it as a return register anyway. Inside our function, we'll store the accumulated product in RAX and the current loop index in RCX. The former will start at 1, the multiplicative identity, and the latter will start at our argument, which is 16 bytes above RBP. We begin our loop. The first thing we do is check whether RCX is less than 1 or not, and if so, we exit the loop. In our previous examples, we've done our repeat check at the end of the loop rather than the beginning, which is more efficient in terms of branches but has a problem. Namely, a loop written in that way will always run at least once, and we want our factorial function to work correctly for all non-negative integers, including 0. If RCX is still at least 1, then we multiply RAX by RCX and store the result in RAX. Remember that the multiply instruction is a bit funny in that it always uses RAX as the destination and left-hand side of the operation, rather than taking two explicit arguments like add does. Additionally, this will store any overflow in RDX. We ignore that overflow in this example, but it still clobbers the RDX register, which is why we saved that at the beginning of the function. Once we've done our multiplication, we decrement RCX and then unconditionally jump back to the top of the loop. At the end of the loop, we pop our preserved registers, then we pop RBP, and then we return. Now, one thing we haven't explored yet is the concept of recursive functions. Like in many languages, a function written in assembly can call itself. When a function calls itself, we say it's recursive. Let's rewrite the factorial function to be recursive rather than iterative. We begin with our usual function prelude, and we'll save the same two general purpose registers we did before. Next, we move 1 into RAX and our argument into RCX as before. Then we immediately compare RCX to 1. If RCX is less than 1, then we jump to the end of our factorial function. In this case, RAX is already the value 1, thanks to our move instruction, so we simply return our base case. If RCX is greater than or equal to 1, then we push RCX minus 1 onto the stack and call the factorial function again. After cleaning up the stack and incrementing RCX once again, RCX contains our real function argument, and RAX contains the return value of the factorial call for 1 less than our function argument. We want to multiply those two values together, so we use the mul instruction, and then we harmlessly let our code fall through to the factorial end label. Note that we didn't have to preserve RCX before making our recursive call, since the factorial function preserves all registers it uses as a matter of course. In the case of the factorial function, it's straightforward to write it iteratively, and an iterative solution is generally more efficient, so it makes sense to go with our former solution. However, an iterative solution doesn't always present itself so readily. Let's take a look at a more complicated recursive function called the Ackermann function. The Ackermann function is an early example of a recursive function that is not primitive recursive. At a very basic level, this essentially means it's difficult to compute the Ackermann function iteratively with basic looping constructs. However, it's straightforward to do so with recursion. The Ackermann function takes two non-negative integer arguments m and n. If m is 0, then the result of the function is n plus 1. If m is non-zero but n is 0, then the function recursively calls itself as a of m minus 1, comma 1. Finally, if both m and n are greater than 0, then the result is the double recursive call, a of m minus 1, and a of m, comma, n minus 1. The Ackermann function grows very large, even for fairly small inputs. For example, a of 4, comma 2 is a number consisting of over 19,000 digits. To be clear, I didn't say the number is over 19,000. I said the number has over 19,000 digits. So naturally, we'll only be using this with exceedingly small inputs. We'll write our Ackermann function recursively. First, we set up our stack pointers. Then we push RBX. We'll be using RAX and RBX here, and we'll return in RAX. So we preserve the current value of the RBX register. Next, we load m, our first argument, into RBX, and n, our second argument, into RAX. We check if RBX is 0. If so, we jump to our base case. Down in our base case, we simply increment RAX, which contains n right now, so that it contains n plus 1. Then we end our function by popping RBX and restoring our stack. This has the effect of returning n plus 1 to our caller, since we return in RAX. Next, if we didn't take the jump to our base case, we check if RAX, or n, is 0. If so, we jump to our first recursive case. In our first recursive case, we call our Ackermann function again with m minus 1 and 1 as inputs, and then we jump to the end of our function, returning the result of the recursive call. Finally, if neither of our inputs is 0, we need to make two recursive calls. We decrement RAX, push RBX into RAX, and call the Ackermann function. This has the effect of calling our function recursively with m and n minus 1 as arguments. The result is placed into RAX. We decrement RBX so that it contains m minus 1. Then we push RBX and RAX and call the Ackermann function again. Remember that RAX contains the result of the previous recursive call, so this calls the Ackermann function with m minus 1 and the result of the recursive call as its two arguments. At the end, we jump to the end of our Ackermann function, as the value in RAX is already our desired return value now. Let's take another look at our original problem. Both of these programs, as well as our original Project Euler solution, are missing a crucial piece: the ability to output the value at the end. We have a function from libc called puts that can output strings, but our result is a 64-bit integer. So we need a function that can take a 64-bit integer and store its base 10 numerical representation in a string. We'll call our function L to string, short for the phrase long integer to string. It will take one 64-bit integer as an argument on the stack, and we'll store the resulting string bytes in a global variable called string. We'll preserve all registers we use, including RAX, since we're not planning to return anything directly. We start by setting up our stack and base pointers. Then we push several registers, including R flags. Let's talk about the algorithm we're going to use. We're going to take our number and repeatedly divide it by 10. As we divide, we'll take both the quotient and the remainder. We'll convert the remainder, which is a single-digit number, into a character and store it in our string. Then we'll repeat the process on the quotient until we hit 0. Finally, we'll have stored the number in reverse order, so we'll need a second loop to reverse the string. Let's see it done concretely. We set RSI and RDI to the beginning of our output string. RSI will continue to point to the beginning, while RDI will advance through the string with us as we proceed. Next, we set RAX to be our input number, then we begin our loop. We need to discuss how the division instruction div works. Recall that multiplication, done with the mul instruction, always took RAX as its left-hand multiplicand, and it stored the result of multiplication in RDX and RAX, with the most significant bits going in RDX and the less significant bits going in RAX. Division acts as largely the reverse of this. The dividend will be the number stored in RDX and RAX together, and the divisor will be in the register we choose. After calling the div instruction, the quotient will be stored in RAX, and the remainder will be stored in RDX. Since our input number is at most 64 bits, we don't need the more significant bits of RDX, so we just set them to 0. We set our divisor RCX to 10, and we call div. At this point, the quotient is in RAX, and the remainder is in RDX. We add 0 hex 30, or the ASCII value of the numerical digit 0, to RDX so that it represents the digit as a character. Then we store that character in RDI, the pointer to the end of our string. Next, we increment RDI since the string just grew in length. Then we compare RAX, our quotient, to 0. If it's 0, we continue onward, otherwise we repeat the loop. At the end of our loop, our string contains the number we want, but it's written in reverse. First, we store the null character in RDI so that our string is null terminated. Then we write another loop to reverse the string. RDI points to one past the end of the string, and RSI points to the beginning. We're going to swap the values at RDI and RSI, then we'll increment RSI and decrement RDI, and we'll continue doing that until the two meet in the middle. Inside our loop, we first decrement RDI since it points to one past the end of the string. Then we swap the characters at RSI and RDI. XCHG, short for exchange, swaps the values at two positions, sort of like move, but in both directions at once. Note that we can't simply write exchange RDI RSI, as at least one of the arguments must be a register, so we move the value at RDI into AL, the low 8 bits of RAX, then we swap AL and the value at RSI, and finally we move AL back into the value at RDI. Finally, we increment RSI and check if the two have met in the middle. If not, we repeat our loop. If so, we end our function as the string has been written and null terminated successfully. Now we haven't considered the special case of the number 0 yet, but as it turns out, the function already works for 0 as written. If our input is 0, then RAX starts at 0. The initial loop still runs once, since the check for loop termination happens at the end rather than at the beginning. Inside, RAX is already 0, so both our quotient and remainder will be 0, and the character 0 will get written to the string. When we exit the first loop, the string will consist of the character 0 with ASCII value 0 hex 30, and our reverse operation harmlessly reverses the string of length 1. And this is the final piece of our Netwide Assembly program that solves Project Euler problem number 11. Here's the full solution once again. Next week, we'll be back on our usual schedule with problem number 12 in this lecture.